At this point, we want to talk about finding the general solution to this equation, where we have the matrix A multiplied by the vector x set equal to another vector b. In other words, we want to find all possible values of the vector x, where if we pick any vector b, that vector x is going to satisfy the equation after we've plugged in for that b. Now, we've looked at the null space as all the solutions to the equation a times x is equal to the 0 vector. So the matrix A times the vector x equals the 0 vector. We know that that's the null space of the matrix A, or that all of the vectors x that satisfy this equation make up the null space of the matrix A. And we talked a little bit in the last video about the equation the matrix A times the vector x is equal to the vector b. And we talked about how that was related to the column space of A. What we want to recognize now is that the solutions to this first system are the complementary solution, or part of the complementary solution, and that the solutions to this equation, the matrix A times the vector x equals the vector b, that is the particular solution. And what we're looking for in this video is the general solution, all of the vectors x that work for both of these, that satisfy both put together. And when we put that whole universe of solutions together, that's going to give us the general solution. So to distinguish between the general solution, the complementary solution, and the particular solution, oftentimes you'll see this null space equation written as a times the vector x, but we put a little n there to indicate null space, and we set that equal to 0. For this second equation, we often put a times the vector x and a little p there for particular solution. We say that's equal to the vector b. And then the general solution is what we get when we add these two together. So when we add these equations, which is a perfectly valid operation, we'll add the left-hand sides and we'll get a times x plus a times x particular is equal to the 0 vector plus the vector b, which is what we get when we add the right-hand sides, so plus the vector b. But if you remember from matrix addition is distributive. So by the distributive property, we can pull out the matrix A and say a times the vector x plus x particular is equal to, and on the right-hand side, we know that adding the 0 vector to any other vector doesn't affect its value, doesn't change its value. So this is the same as just saying the vector b. And this is why we say here that the general solution, which we call just x instead of x sub n or x sub p, the general solution is equal to the sum of the null space solution plus the particular solution, because we can see that this vector, when we add these two vectors together, we get the sum of them, which is also itself another vector, that satisfies this ax equals b equation. So this is the general solution. This is the one that we're looking for and the one we want to try to find in this video. So the easiest way to see that is just to walk through an example so that we can see what it looks like to find the solution to the null space equation, then find the particular solution and add those together to get the general solution. So let's say we're given a matrix A, and that's going to look like this. We're going to have 1, 2, 0, and then maybe 2, 3, 5, and then 4, 6, 10. And normally this would be the matrix here, but our first step is going to be to put this matrix into reduced row echelon form. And later on, when we find the particular solution, we're going to need to augment this matrix with the vector b. And so we'll say b1, b2, b3. So while we're putting this matrix into reduced row echelon form, let's go ahead and augment it with b so that we get that step done at the same time, because we can either do it now while we're getting this into reduced row echelon form, or we'll have to repeat the process and do it later. So let's just combine those two steps into one. So to get this into reduced row echelon form, the first thing we want to do is take 2 of row 1 away from row 2. So we'll say row 2 minus 2 of row 1, and that's going to replace row 2. So row 1 is going to stay the same, 1, 2, 0, and then B1. Row 2, we're going to take 2 of row 1. So 2 times 1 is 2, and then 2 minus 2 is 0. 2 times 2 is 4. 3 minus 4 is a negative 1. 2 times 0 is 0. 5 minus 0 is 5. And then here we have to do the same thing. So we want to take B sub 2 minus 2B sub 1. Then let's go ahead and zero out the 3, 1 entry as well to make this 4 into a 0. So to do that, we'll take 4 times row 1, so 4 times row 1. We'll subtract that from row 3, so row 3 minus 4 times row 1, and we'll use that value to replace row 3. So 4 times 1 is 4, 4 minus 4 is 0, 4 times 2 is 8, 6 minus 8 is a negative 2, 4 times 0 is 0, 10 minus 0 is 10, and then here we'll get row 3, which is B3, minus 4 times row 1, which is B1, so minus 4B1. And now we've got the first column done. We have our pivot entry, and then we've zeroed out the rest of the first row. Now for the second row, we can just multiply through by a scalar of negative 1. When we do, that'll turn that into a positive 1, this into a negative 5, and then we'll get negative B2 plus 2B1. Now we'll work on zeroing out the rest of the second column. So we want to get rid of this 2. We want to turn that into a 0. So in order to do that, we'll take row 1 and we'll subtract 2 of row 2, and we'll use that value to replace row 1. So 2 of row 2 here, 2 times 1 gives us 2. 2 minus 2 gives us a 0. So we end up with 1, 0. And then here, 2 times a negative 5 is a negative 10. 0 minus a negative 10 is 0 plus 10, so positive 10. And then over here, we get row 1, so B1 minus, we'll get 2B1 minus B2. Then we'll leave our second row the same, 0, 1, negative 5, and then we'll say 2B1 minus B2. And then for the third row, we'll say the third row, R3, plus 2 times row 2 is going to replace the third row. So 2 of row 2 here gives us a positive 2. Negative 2 plus positive 2 is a 0, so 0. And then 2 times a negative 5 is a negative 10. 10 plus a negative 10 is 0. And then here we take row 3, so B3 minus 4B1, and then we add to that 2 times row 2, so plus 2 times 2B1 minus B2. And now we've got our second column complete. Let's go ahead now and simplify these right-hand sides really quickly. So for this first row here, we have B1 minus 4B1 plus 2B2. That's going to give us a negative 3B1 plus 2B2. So here we could get rid of this value here. So get rid of all of this, and we'll replace it with this value that we just found. So we'll say that this is negative 3B1 plus 2B2, and then we can get rid of this here. And then for the third row here, we'll get B3 minus 4B sub 1 plus 4B1 minus 2B2. We'll get our negative 4B1 and our positive 4B1 to cancel, and we'll be left with negative 2B2 plus B3. So we can go ahead and get rid of all of this portion here. Just get rid of all of this. And then we can replace that with this negative 2B2 plus B3. And then we can get rid of all of these calculations here. And then we will simplify the matrix like this. Now to find the complementary solution, the vector x sub n, that's what we're looking for first. We ignore these b's here. Those are going to come in handy later. but we don't need them right now. Now we need to imagine that we have this same augmented matrix, but augmented with zeros on the right. So 1, 0, 10, 0, 1, negative 5, 0, 0, 0, and then augmented with the 0 vector. And then we want to pull out of this a system of equations. So if we say that our columns here are x1, x2, and then x3, what we notice is that x1 and x2 are pivot columns because we have our pivot entries, and x3 is a free column. So we want to set this up as a system of linear equations. So we'll say 1 times x sub 1, or x sub 1, plus 0 x sub 2 plus 10 x sub 3 is equal to 0. And then from the second row, we get x sub 2 minus 5 x sub 3 is equal to 0. The third row doesn't give us anything in terms of a helpful equation. Then we want to solve this system for the pivot variables x1 and x2 in terms of the free variables. So anything that's a free variable, move that to the right-hand side. We end up with x1 is equal to negative 10 x3, and x2 is equal to positive 5 x3. From this, we can write a linear combination equation where we say the solution x1, x2, x3 is equal to the free variable x3 multiplied by, here we said that x1 is equal to negative 10 x3, so we say x1 is equal to negative 10 times x3. We said x2 is equal to 5x3, so x2 is equal to 5 times x3, and then x3 is just equal to x3, so we have a 1. x3 is just a free variable. We could replace that with a generic scalar. So we say then that the complementary solution, the vector x sub n, is equal to some generic scalar, we'll call it c sub 1, times the column vector negative 10, 5, 1, and that is the complementary solution. And now, because we've done all this work up front with the b's here, we can pretty quickly find the particular solution. So to find the particular solution, you want to start with this last row here, if you have it, where you have all zeros across the bottom, and then this value over here on the right-hand side. Because what this really tells us is that 0 is equal to negative 2b2 plus b3. If I add 2b2 to both sides, I get b3 is equal to 2b2. Now I'm just looking for any combination of b1, b2, and b3 that satisfy this equation. So for instance, if I pick b2 is equal to 1, over here on the right-hand side, I'm going to get 2 times 1 is 2, so I'm going to get b3 equals 2. So b3 equals 2. This combination satisfies this equation, but I also need a value for b1 that goes with this. Well, the only value for b1 that makes sense is 0, because b1 isn't represented here. If you imagine if I added b1 somewhere into this equation, which I can't do, but if I could, that value would have to be 0 because this part is the true equation. I can't put that in there. So the only thing that makes sense for b1 in this equation is 0. So now I have this combination b1 equals 0, b2 equals 1, and b3 equals 2. I want to plug those back in to this augmented matrix here so that I can get some real values for the right-hand side. So that matrix is going to look like this when we rewrite it. We're going to get 1, 0, 10, 0, 1, negative 5, 0, 0, 0, and then we're going to augment that. Over here on the right, we said b sub 1 is 0, so this term goes away. B sub 2 is 1, so 2 times 1 is 2, and we get 2 here. B sub 1 is 0, so this term goes away. B sub 2 is 1, so we get a negative 1. And then here in the third row, b sub 2 is 1, so we get negative 2 times 1 is a negative 2, plus b sub 3, which is 2. So negative 2 plus 2 is a 0. And that makes sense. We should get a 0 there because we found the values of b sub 2 and b sub 3 that made this last row true. And we said that this had to be equal to 0. So we have to have this 0 value at the bottom. So we have a full 0 row. And now from here, we write a system of equations. Remember, we're driving toward the particular solution. So here, again, we get x1 plus 10 x3 is equal to 2, we get x2 minus 5x3 is equal to -1. Now at this point, we want to set any free variables equal to 0, because remember, we're allowed to set the value of the free variable equal to anything we want to. So let's pick a convenient value, like 0. If we set x sub 3 equal to 0, since x sub 3 is the free variable, then here this first equation is going to give x sub 1 plus 0 equals 2, or just x sub 1 equals 2. And then the second equation will give x sub 2 minus 0 equals -1, or just x sub 2 is equal to -1. Remember, we said that x sub 3 was equal to 0. We set it equal to that value because it was a free value. So this gives us here, if we put these together, this gives us the solution to -1, 0 as a column vector. So we can say then that the particular solution, which is the vector x sub p, is equal to this exact vector here, 2, -1, 0. And then the general solution, or we also call it the complete solution, is just the vector x, and we take the sum of these two, and we always list the particular solution first. So it's going to be the vector 2, -1, 0, and then we add to that our complementary solution. So c sub 1 times the vector -10, 5, and 1. And then this whole thing here, this vector x, this is the complete solution, or the general solution, to the equation ax equals b when we start with this 3 by 3 matrix here.